Hello guys, welcome back to my channel ES Study. Today we will learn one of the important topic in computer science and engineering as well as data structure, which is Huffman coding tree. So let's discuss why Huffman coding tree is important and how it works. So suppose we want to send a text message from a sender A to receiver B over the network. So how can we send the string message or text message? We need to convert it to 01 string. So we know that every character is a sequences of zeros and ones and stored using 8 bits. So if we want to send A through the network, we need to first convert it to the string as zeros and 1. So we need to represent this with 8 bit. Like that, we know the ASCII value of A is 65. So the binary representation of 65 is 1 0 0 0 0 and 1. So we represent this binary representation here, and this is the 8 bit. So for each character we want to send over the network, we'll have the bit length of 8. So if we have 5 characters in our message, we need 40 bits length. However, we want to compress the data to avoid the total storage. So in computer science and information, a Huffman code is commonly used for lossless data compression. So in that case, we can use the Huffman coding tree for lossless data compression because we don't want to lose our data. And this technique does the most frequent character gets the smallest code, and the least frequent character gets the largest code. This example, suppose we have a message with characters A, B, C, D and E, where A appears 15 times, B appears 7 times, C appears 6 times, D appears 6 times and E appears 5 times. So if we build a Huffman coding tree using these characters, so we'll get the Huffman coding tree in this pattern, where only one bit string represents A, which is 0. The character B represents by 3 bit string. Character C represents by 3 bit string. Character D represents by 3 bit string. And character E represents by 3 bit string. Now, if we want to pass this message over the network from source A to receiver B, we need total here the number of characters A 15 times, B 7 times, C 6 times, D 6 times and E 5 times. Total 39 times. So we need 8 into 39, 312 bits. So this is too much. However, if we use the Huffman coding tree, and where the code word for A is 0 and for B is 100 here, for C is 101, for D is 110 and for E is 111. Now we need only how many bit string? For A is 0, that's mean only one string, 1 bit. So there are total frequencies 15, so we need 15 bit string. Here is 3 bit position, and for B the frequency is 7, so we need total 21. Here for C is 3 bit and the frequency for C is 6, so we need total 18 bit length. Here for D we need 3 bit length, and for D the frequency is 6, so we need total 18 bit length. And for E we need 3 bit string or bit length, and its frequency is 5, so we need total 15. And if we sum of this value, we eventually need only 87 bits. That means with only 87 bits we compress this information. However, this information will be looks like, for example, ABC, for message ABC, A we represents with 0, B we represents with 100, and C we represents with 101. So it will be like in this pattern, and total bit length will be 87. Encoded bit length is only 87 bit, which is much lower in compared to the original bit length. However, in the receiver side, if the receiver want to decode this message into the original string, so the decoder needs this tree as well. That's why the sender needs to send this tree as well. So in this tree, what the sender needs to send is that the sender only sent the characters like that A, B, C, D and E. So it needs for representing A, and in ASCII value is 65, so it needs 8 bit. Similarly for B, 8 bit, C 8 bit, D 8 bit and E 8 bit. And for its frequency 15, it needs another 4 bit. For B, it needs another 4 bit for its frequency. For C, similarly 4 bit, 4 bit and 4 bit. Because here the frequency number in the range from 5 to 15, which we can represent is number into a 4 bit string. So we need total for each character is 12 bit, and there are 5 characters, so we need 5 into 12, 60 bits. And this 60 and this 87, so we need total 7 and 147 bits length, which is much lower, almost less than the half value of 312. So it is more compressed form. The question is that how can we develop this Huffman coding tree, or how can we build this Huffman coding tree? So to build Huffman coding tree, we need to follow some steps. So let us start with building a Huffman coding tree. In the first step, find the frequencies of each symbol occurring in the message. So we need to find the number of frequencies of each character in the message. So let's do these steps with an example. So suppose the string containing 22 characters. Here is a string, and we need this string sent from station A to station B over the network. So to send this character string, we need to convert this string into 0-1 sequences. So as we already know, to convert each character, we need 8 bit string length. So the total bit string need in this case is 22 into 8, which is 176, and is much longer. So we want to compress this bit string length using the Huffman coding tree. Now we built the Huffman coding tree. So in the first step, find the frequencies of each symbol occurring in the message. So here is already given. The frequencies for A is 9, for frequencies of B is 4, for frequency of C is 5, for frequency of D is 3, and for frequency of E is 1. So in the second step, begin with a forest of single note trees. Now we need to rearrange these frequencies according to increasing order. So in first, here is 1 and the for the character E, and the frequency is 3 for character D. Then the next frequency is 4 for character B, then the next frequency is 5 for character C, and finally the next frequency is 9 for character A. Now begin with a forest of single node trees. So here is a forest because is represents a single node tree. So many trees made the forest, and is contains a symbol and its frequency, where is character contains its symbol and the frequency, or is tree represents a symbol and its frequency. Now we have to do recursively the following two steps. So the recursion or recursive means we need to do the same tasks again and again. So select two trees with the smallest frequency at the root. So we have to select two trees with the smallest frequency in the root. So here the smallest frequency is E and D, which is 1 and 3. So in next step, produce a new binary tree with the selected trees as children. So we need to produce the new binary tree with the selected trees. So here is the new binary tree, where is in the left child and D is in the right child, but we can't alternate this. We can put the D is in the left child and is in the right child. It doesn't matter. So the order is not important here. Now, and store the sum of their frequencies in the root. So we need to store their sum of their frequencies. So here is 1 and here is 3. So 1 plus 3 equal 4. Now we need to do these steps recursively. Now we need to find the next smallest trees. So here is 4 and here is 4. Here is 5 and 9. So the next two smallest trees are 4 and 4. So we need to make a new binary tree with these trees. So here should be 4 and B, and we should remove this one and put the sum of their frequency at the root, which is 8. Now we search and look for next to smallest frequency at the root. Here is 8 and here is 5 and here is 9. So the next to smallest are 5 and 8. So we should make another binary tree using these two trees. So here should be 5, and we should remove this one, and the node value will be 5 plus 8, which is 13. Next, minimum is 13 and 9, so we should add up these two, where here should be 9 and it should be A. The summation of these two frequencies is 22, so we should remove this 9. Now we construct or build the Huffman tree. So we need to put the code either 0 or 1. So according to Huffman coding tree, we should put 0 in the left edge or 1 in the right edge, or alternatively we can put 1 in the left edge and 0 in the right edge. However, we should follow the same pattern in all the edges. So here we should put 0, here is 1, here is 0, here is 1, here is 0, and here is 1. So we can now represent the character A with the bit 1, because here from the root we reach to A with just one edge, which represents by 1, and to represent C we need the code words 0, 1. To represent B we need the code word 0, 0, 1. To represent D we need the code word 0, 0, 0, 1. And to represent E we need the code word 0, 0, 0 and 0. So to send this message, what we need to do, we need to just replace the character A with its code word. So here should be 1, and then A for 1. For B our code word is 001, so 001. For A, our code word is 1. For B, 001. So in this fashion, at the end we will get 1 1. The total length for this string will be, here for character A we need only 1 bit, and there are 9 S, so we need 9 bit. For C we need 2 bit position, and here the frequency for C is 5, so we need 10 bits. And for B we need 3 bit position, and here in B the frequency is 4, so we need total 12. For D we need 4 bit string, and the frequency for D is 3, so we need another 12 bits length. And here E we need 4 bits, and the frequency of E is just 1, so we need only 4. And eventually when we sum up these values, we will get 12 plus 12, 24, 4, 28, 38 and 9, so it's 47. So this string length, the bit string length will be 47. Now when the sender sent this 47 bit string length, the sender also sent this tree information to the receiver. Otherwise the receiver cannot decode this message. So what will the sender will send? So the sender sent this string, as well as the sender sent for A its binary representation with 8 bits. So we know for character A the ASCII value is 65, so we can represent it like that. So 1 0 0 0 0 0 and 1. Here in left side is 0, because in 65 we can represent with 7 bit position, so we fill the 8 bit position with 0. So what we will send for A, 8 bit, and for the frequency, here is the frequency is 9, we will send another 4 bit, where the 9 we can represent with 1 0 0 1. So we need to total send 8 plus 4, 12 bits for A. Similarly for B we need to send another 12 bits position. For D we need to send another 12 bits position. For E we need to send another 12 bit length. So total bit length will be, there are 5 characters and frequency, so it will be 12 into 5, 60, and here is 47 bit length. Now we need these two in a separate file. So when the receiver get this bit length, the receiver will generate the same tree using the Huffman coding tree. Now the receiver has this 47 bit length information, so the receiver will decode now. So for 1, when the receiver get 1, so the receiver start with the root and go to the path 1, and when when the receiver gets any character, just print it. So the receiver gets A, so print the A here. Then the receiver go for another 1, so in 1 receiver get A, so receiver print A. Then the receiver start with root and go to 0, and then 0, and then 1. So ultimately the receiver will print when eventually find a character. For the next one, again 1, so the receiver will just print A and A. So when the receiver go any branch of this tree and ultimately get any character, the receiver will print, and ultimately the receiver will get this original message. So this is the very important topic in computer science and engineering, as well as data structure. I think all of you understand clearly. So in next slide, just pause the video and try yourself in this example, where the question is that can we find the code word for each character in the following text using Huffman coding tree. So the text is I am an engineering student, so you have to find the code words for each character using the Huffman coding tree. I hope all of you understand this important topic. Still, if you have any queries, please leave your question in the comment box. I will try my best to answer all of your queries. Thank you very much for watching this video. Please like, comment and subscribe my channel.